Students, welcome back to part 2 of lecture number 2. So, we have discussed quite a lot about how material can be designed, right, traditional way, trial and error, as well as how data informatics can be important. Let us look back little bit, not much, we will not much discuss about it. Let us look back, how do we discover a new materials? What do you think about it? Let us start from the earliest 40,000 BC or even 25,000 BC, when human just started living on this earth. Human did not have much, right, except naturally available materials like stones or maybe some other things, metals like silver, gold, which were native metals available on the earth crust. So, human were making or human made the sharp devices or sharp objects to kill the animals, mostly made of stones. But in something around 20,000 BC, what is known as a pottery came into picture. You can see here, pottery was very important, because with pottery you could have used make objects like cooking utensil, or even other things also you can make it. Okay, tiles can be made of pottery also. So, that is very important, but that did not change much the history of science or materials, right, till somebody accidentally discovered bronze. Bronze is a copper and tin alloy about 10,000 BC, and many people say it was discovered in Indus Valley civilizations. Accidentally it was discovered, maybe because of some explosion or something happened, or some igneous activities of volcano, something happened that led to that. So, then came the Bronze Age. A lot of objects are made up of bronze, swords are made up of bronze. Okay. But after that we have Iron Age. We mastered the art of making iron from the iron ore, and that is what India was very famous. Best of the best iron ores were available in southern part of India, in Karnataka and Andhra Pradesh, and this was all reduced by a process, and a steel called wood steel was produced something around 12,000 BC, and that changed the whole thing. Iron was strong, iron was very ductile, so iron was used to make swords, knives, all kinds of warfare objects, and that changed everything, right. That is how these metals came into picture and changed the whole dynamics of civilizations. And then in the modern days you have concrete, steel, ceramic tiles, space vehicles, silicon, that is why computers, laptop, mobile phones, everything is there, came into picture, and plastics came last 50 to 100 years, okay, 50 to 80 years. Okay. This is in a nutshell materials discovered, very small portion of the material I am talking about it. Now, Michael Ashby has given a chart, materials across the ages. You can see here how material has been used starting from 10,000 BC to till 2020 or even more, right. So, you can clearly see different alloys came, gold, copper was at the time used, copper is bronze, as you see, iron, cast iron, steels, alloy steel, light alloy, super alloys, titanium alloys, and so many different materials are discovered in case of metals. Similarly, in case of polymers, you have stone, flint, pottery, glass, cement, Portland cement, silicas, tough ceramics, engineering ceramics, alumina, partially stabilized zirconia, etc. came into picture. And in case of composites, hell lot of things came into picture. You can see here glass fiber composite, carbon fiber composite, metal matrix composite, ceramic composites, all came into picture. But you must be thinking how these were discovered, right. So, are they discovered by accidental way, or are they discovered in a systematic way? That is what we talk about it. So, how do you discover materials? First is very simple, intuition based. You think of something, you have intuition, you go ahead, synthesize that material, do some test, okay, and find out it works. That is what is done. Cement was discovered in this way only. Nobody has thought of discovering cement and systematically done the research to do that. It is discovered based on a systematic manner, right. Many materials were discovered. Steel was also discovered like that way. When steel was discovered in those days, people did not know that it is steel or something else. But there is another way of discovering material, that is called serendipity. Serendipity means accidental discovery, okay. It is called accidental discovery. This is not only true for material, it is true for many things. The first antibiotic, penicillin, was discovered by the way, and you can go and find out in Wikipedia how it was done. Please do read about it. Serendipity is very important aspects. It is a surprise. We want to do something, but we get into something else. That is what is called accident, right? An accident can lead to discovery. So, this here I am showing you glass ceramics. You have a ceramics, you have a glass in which you can build in ceramic nanoparticles. Glass is brittle, as you know. If you throw stone, glass will break into pieces, but glass ceramics will not break, because these nanocrystals will absorb the energy of the cracks and stop the cracks to pass through. So, glass ceramics become a very important material. It was discovered by Dr. Skutke in 1953 after letting a piece of glass in a furnace overnight by mistake. So, a piece of glass is a frozen thing actually, okay, it is a amorphous structure. Dr. Skutke put the glass accidentally in a furnace overnight, and next day morning he came and saw some portion of the glass has crystallized and formed this nano ceramics. And that is how actually glass ceramics are discovered. There are many such examples I can give you. Quasicrystals were discovered, bulk metallic glass was discovered. So, therefore, it is one of the ways to discover materials, but then you have to be lucky, you must be lucky. You must also know that you have discovered something new, that is why it can be done. This is not the case which can happen to everybody. Then come trial and error approach. I write T and E, okay, trial and error. You try, fail, again you try, again you fail, and many times you do, then you succeed. You know, when Edison, Sir Thomas Alva Edison, when he was making the bulb, okay, electrical bulb, in 1890s sometime he has succeeded. He tried more than 3,000 designs of the bulb between 1878 and in 2 years time. He tried many ways and then he got succeeded. That is why it is called a Edisonian approach, trial and error. This is one way of discovering new materials. You try hard and make a discover new materials, correct. So, what do you understand? One is intuition based, other one is you have to be lucky to have an accident and good accident, discover material, and third one is trial and error, which is people like me or you normally use, right. But that is not the end of it. Can I use data to discover new materials? Is it possible? So, let us talk about a little bit about that. From the paper by Ankit Agarwal and Alok Chaudhary, they has written nicely that first paradigm of any discovery was basically purely experimental based, and there we were using empirical science, empirical equations. We did not know how the equations were coming, what are the concepts are coming, we simply were using empirical equations to discover something. That is before Isaac Newton, below 1600, okay, before Sir Isaac Newton came into picture. But after that we have a second paradigm of material discovery or anything discovery, that was based on models and theoretical science. Okay, if you look at Newton's laws of motion, gravitational law, everything is based on what? Based on certain model, certain theoretical framework. Thermodynamics actually is based on that. The laws of thermodynamics are basically based on this. So, this was done, that includes quantum mechanics also, almost for 350 years. That is why most of the scientific foundations were done, remember this. But from 1950s onwards, computers came into picture. In fact, 1940s and onwards, computers came into picture thanks to IBM and other organizations. And 1950s and 60s, computers become available to people and with some reasonable computational power, and we started doing what is known as a computational science, what is known as simulations, and that make a new paradigm. And nobody is doing only experiments, everybody is not doing experiments or model based theoretical calculations people started looking into computational aspects of that, and that is what actually what led to simulations, this concept of simulations, and we see the development of density functional theory, molecular dynamics, which are based on Newton's laws of motion. That is what is called a third paradigm in the sense of that. So, therefore, we simply go from empirical science to model based science to computational science. Is there any other paradigm? Of course, yes. After 2000, what we have is a big data driven science. Okay, that is what is called informatics or data science, and this is what is known as fourth paradigm. You and me are living in that paradigm. Whenever you search anything on your Google or on your Facebook or whatever, Instagram, people are using data science, people are using big data, and if you search something today, tomorrow, day after tomorrow, they will know this is what is your favorite, and then they will feed you more, right? That is what happens. You can check yourself and find out that, and this is basically uses predictive analysis, relationship mining, sometimes anomaly detections, and we are going to focus our whole course on these aspects, how the data science can be made use for material discovery. So, now I put it here again, taken from Ankit Agarwal and Alok Chaudhary's paper on APL materials, from first to second to third to fourth paradigm. Now comes 1920s, 2020s or 25s. Can I make the material discovery fast, very fast? Normally it takes 25 years to discover a material and then apply it in real applications. Can I reduce the cycle time to 10 years or less? That is what is called accelerated discovery or accelerated scientific methods. This requires you to use AI tools, machine learning as well as informatics. So, this is what it is, correct? So, you can have data from experiments, simulations, all kinds of data, composition data, processing data, structure data, properties data, papers, reports, whatever you want, you can get data. So, once you get a data summary, you can identify key factors, predict properties, discover new materials. As you can see here, so what you do is, you have databases are basically created from the data, then you can do data preprocessing and extractions, you can do data reduction, simply dimension reduction, you can do modeling, that is what is called machine learning or deep learning, you can evaluate it whether your modeling is good or not, finally you can accrue knowledge out of it. That is what is to be done. So, and therefore, important aspect is first and foremost is data, then you can actually do extraction, processing, reduction, modeling, whatever you want. That is the key aspects of that. So, in the traditional approach, what is called the first, second and third paradigm, I have shown you, we are all doing experiments or simulations, correct? We do not want to do that anymore. We want to take this data, collect the data, whatever experiments, simulations, computational approach has done, and take this data to build a database. And then from the database, you can use a machine learning model to discover new materials. That is what is called data driven approach, or that is what is called as a fourth paradigm, or what is called as a big data paradigm. Okay. So, we are into that big data paradigm, and remember, this is going to change the whole concept of discovery of anything. Please remember that. And it has this paper by Hinaman et al. It's very interesting. You can read it and understand it. Okay, so we talked about data, right? First thing I told you, right? The data are important. Whether data are available to you, or are there enough data to do modeling? That is the question you have to ask first. Do I have data available everywhere? Like I go to a river and I can find sands, so much of sand. I do not have to worry about it, right? I can just collect it and use it. Is it same for the data in the material design of discovery? And do I have enough data? Is it infinity large, very large, large, small, whatever is the situation, okay? So, as you see here in material science, we focus on that. We already have some data, Let us talk about material property data, material behavior, basically talking about physical properties, mechanical properties, functional properties, correct. We have books which can compile data like ASM handbooks, American Society of Metals, okay. This is actually American Society for Metals handbook. Then you have Smith's handbook. You can see it on the net. They actually compile all the data after checks and balances and give it to you. That is nothing but a database, right. Then you can also have a crystallographic database that will tell you crystal structure data of inorganic, organic materials. That is what is known as a Pearson crystallographic database. Pearson database. In addition, you can also have thermodynamic databases like data of free energy of different phases, Cp, heat capacity, heat of formation, etc., etc. This all exist. Remember this. This all exists for last 30-40 years. We know that they are all data, and mind you, these are all not small data. It is a huge data. Okay, not hundreds of data. It is like 1,000, 10,000. Sometime it is more than that amount of data, especially crystallographic and thermodynamic databases. Now, one can also make their own data. That's called a curated database, self-made. You can collect data from different sources and make data. Like you have, on a new material, data may not be available. You can collect all the papers, published paper, reports, everything, and use a, natural language processing, okay, kind of a model, and collect data and create a database. That is what is called a curated database. Remember that curated database. Let us discuss each of these separately. This is what I showed you this particular plot, right, the last, part of my lecture part, lecture 2 in the last part. So, as you can see here that this is the mechanical property data of all steels, tensile strength, elongation data. This is a chart. Huge amount of data was used to make this chart. You can extract the data out of it from the chart easily. That is what is called material property data. This is true for any kind of properties, mechanical, physical, functional, whatever you can think about it, all are available. Michael Ashby is, I refer to him quite a lot. Not only that I like him, but he has done a phenomenal aspects. He has already given this chart, what is known as Ashby chart or material property chart. They were made by using data only, right. And remember, this was made in 1990s. First time the book was published by Michael Ashby is 1996 or 94, I do not remember, but that is in 1990s. In those days, nobody was talking about informatics, data science, but he actually made use of data to make these charts. His book has all these charts which can be used for design. So, that is nothing but a data, right. Crystallographic data, there are two types of crystallographic data. One is open crystallographic data, other one is you have to purchase it, right. As you know, long term data preservation in crystallographic data was started very early. There is a thing called International Union of Crystallography, and the crystallographic community actually collect data and then compile the data. These are the different books. Nowadays you can get even CDs or pen drives also get the data. This website will give you all the different kinds of databases. You can also have open databases. Anybody can use it, right. That is what is the theme nowadays. Can I keep my data open to everybody, so that everybody can see the data, use it, curate it, check it, balance it, whatever they want, right. That is what is called COD, crystallography open database. This website crystallography.net/CODs will give you insight of this kind of data available. Biologists keep a lot of their data in open databases. We material scientists are not so much, but biological scientists, they are keeping the data in the open database. Thermodynamic databases obviously uses, we use CalFARD, there is a D missing here. CalFARD is nothing but a calculation of phase diagrams, where you need a lot of these data, huge amount of data required to that. This approach of CalFARD allows you to prediction of the phases and microstructures in the systems, multi-component systems, where data can be obtained from critical assessment of binary, ternary subsystems. Okay, it is very similar what we do in the labs now. Curated databases. It is a repository of data that has been carefully selected, organized, managed by somebody or set of people to meet specific needs of the interest. These are populated and updated with a great deal of human efforts. One example is what? SEM Digital Library. You can look at this website, find out that. Most of the reference work like dictionary, encyclopedia, gadgets, they are actually, you used to find references in the libraries, you can find out they are actually nothing but curated databases, right, dictionary. And SEM Digital Library actually provides you a lot of databases. Are the data enough? I am listing you different kinds of websites where data are available. You can see some are public domain available, some are open access, and some are subscription based also. You have to pay money to get it, right. So, therefore, these websites will give you what kind of material property or structure database available, you can get it, because you need to model the using data only. COD, that is what is called a open databases. Records have been increasing a lot. You can see here from 2003 to 2019, huge amount of data are now put it on the open databases, and it will happen more and more so, because informatic data science will change the way we actually do discovery of materials. Another important aspect is the data from microstructure. You know, material scientists handle a lot of microstructures, and microstructures are the key for material science, and data can be at different length scale. Like here, this is micron level, this is Armstrong level, right? You can see here 0.31 nanometer is nothing but 3.1 Armstrong, right? So, this is atomic level 3.1 Armstrong. So, we can actually get a lot of data out of it. We can actually make a lot of data out of it, by the way. They exist, correct? You can see that in the real life, real world. So, you can do that, and that is what is the idea. And there are different kinds of microstructure, different length scales. This is perlite, you can see here. So, there are many types of microstructure exist in the literature. You can get it and do that. A lot of data can be extracted from it. So, finally, what is the goal? You have data from experiments, models, simulations, microstructures, correct? Data will provide you trends in the process structure property linkages, that is nothing but information, correct? From data you can get information, right? Simply if you want to use Google Maps when you are traveling some places, what do you have is a map. You should know how to read the map to get the information, right? But information will gives you knowledge, remember that. And knowledge is what is important, that is what drives the civilization. The societies or the countries which have more scientific knowledge, they are superpower, they have more technological, technological sound systems, they are rich. So, therefore, knowledge is important. So, you can obtain knowledge from data and informations. And finally, from knowledge you can gather wisdom. We call it the sage, they are the most knowledgeable person, they have a lot of wisdom, and wisdom will allow you to find out underlying processes what is happening when you make a material or do something. So, this pyramid is very critical in material discovery. So, therefore, at the bottom of this pyramid what happens is the data. That is what we discussed a lot in the last 10-15 minutes. At the bottom of the pyramid you have data, and you have to know how to process the data to get information. So, as you know, this is what is the recent map of data infrastructure. This is on the world map. I do not know whether you can see probably. US and Europe has the largest data repositories infrastructures. India has only one, probably in southern part of the country. Japan, China has some part. Okay. So, you can see Israel has something, but mostly they are focused on Europe and US. This has to change, otherwise data will not be accessible to everybody. So, once you have data, you have to process data, that is what you need the models, right. And as you know, the AI has come because of data actually. AI is what? AI is the ability to machine of computers to mimic human decision making process or problem solving capabilities. Right now this is limited, but we want to make it as much as possible. And under this AI you have two important aspects, one is called machine learning, where you use a structured data. Structured data means data which has both the columns of input and output. And other one is the deep learning, where you can use unstructured data like in form of text, images, videos, whatever, you can do that. So, these two actually together form the AI domain. So, ML is a process by which machine can automatically learn from the existing data, remember that, but that is not so easy. Okay. We learn from experience, right. When you learn to walk at the very young age, we fall on the floor and learn from experience, and then we can actually develop a tendency to that. And you know, AI actually can do a lot of things. It can allow you to, you know, like it has observation ability, analytical ability, problem solving ability, learning ability, all these things are built in many of these AI tools, all of you know. If you want to know more of this thing, please enroll in my course on AI, ML and materials engineering, you will understand that. I do not want to repeat everything from there. Right now we are using narrow AI, like you can use detecting faces, plug-in contents online, customer care, online chatbots. General AI is still a dream today, and it will be able to, if it is developed, you can do whatever a human can do actually, that is not possible so far. Right now we can do speech recognition, customer service, computer vision, recommendation engines, automated stock trading, many things you can do AI. Okay. It is a game changer, and it is going to be about $15.7 trillion business by the end of this decade, and it will boost the GDP. It will the most important aspect will be in China and North America. They will be the greatest economic beneficiaries of these AI systems, but we should not be far behind as a country. In India, we should also be able to make an impact on that. And as I said, the main important aspects of AI is a machine learning. It is a computer based program, and you know, it is a program which can learn from experience with respect to certain class of task. We cannot learn any task at that moment, and so you define a task, and then it can learn from the task. By doing the task, it can learn from the experience and with certain performance. Like if you are suppose learning how to walk on the floor, your performance parameter will be how many times you are falling on the floor before you learn completely to walk on the floor, right. That is what it is. I was talking about skating on the ice, okay. And so your performance parameter depends upon how fast you can move on the floor without falling off, right, without having accidents with your fellow workers. That is what is the performance parameters. And experience is coming in the form of data, remember this. Data is nothing but a set of records, and each record actually tells you a sample. So therefore, important aspect is that we have to obtain a lot of data to train or to learn. So we always put data in terms of x and I, x and y I. Xi is your input, yi is your output, and xi is called as input, yi is called as a response or level. Some people call yi as a response or level, okay. Some people call it, and you know, it is a very important process. Formal definition is for certain task we have to get some experience, and it is evaluated in terms of performance. First is in the steps of ML, you gather data and do the data engineering or feature engineering. You build a machine learning models, get some insight of the model, and then you can visualize that. That is what is the machine learning model. So let me stop here. So this is what we are going to discuss further. In the next class, we will start our first model, first data, machine learning model is called regression, simple regression mathematical stuff. So we will discuss about that. Thank you.